Every aircraft begins as a problem, a question posed in the dark. Stealth is first achieved through geometry, angles that refuse to return a clean radar echo.
Seams are judged in microns. A single tooth's misalignment can betray stealth. The aircraft is assembled virtually to Every module is aligned before metals meet.
Robotic deposition paths are defined here. Fiber orientation and overlap are mapped to every tooth of the skin. Predictive analytics pinpoint risk flight. Mitigation is enacted before a single part is produced. Interfaces are engineered tooth by tooth. Coatings and adhesives are specified to prevent galvanic or structural mismatch.
Wiring, sensors, and avionics are routed in the model. The jet's nervous system is planned to the last connector. Validated to the last tooth garab. The digital twin is authorized to become reality. Molds are meticulously cleaned and release coated. Any contamination shows up as a flaw on the finished skin.
Robotic layup deposits toes with micrometer accuracy size. Fiber orientation, overlap, and stitch are defined for each load-bearing tooth. After layup, parts are vacuum bagged. A pressure differential and heat in the autoclave consolidate resin and remove voids. The cure cycle raises temperature and pressure along a controlled ramp. Resin viscosity falls, fibers lock, and voids collapse. Robotic drilling ensures hole positional accuracy to spec rec. Every fastener location is machine-controlled to preserve aerodynamic continuity. Titanium billets are heated to forging temperature and shaped under high-tonnage presses. Forging refines grain and creates a robust blank. Heat treat cycles relieve machining stresses. Shot peening improves fatigue life by inducing compressive surface stress. Interfaces are plasma cleaned and primed. Metered adhesive beads are applied to precise bead geometry flume. Bonding is as critical as the parts themselves.
Every finished component is verified, serialized, and released to the assembly line. The digital thread remains.
This is the mate bay, where massive sections are brought together with millimeter control and laser precision.
Laser trackers measure positional data to microns forward.
Alignment is quantified, not guessed. Microshims manage local geometry. Each insertion trades gap for continuity until the surface is flush. Robotic cells validate program offsets and timing. Dry runs prevent damage to composite skins. Clamping applies controlled squeeze to activate adhesive continuity. Pressure is staged to avoid flow or starve zones.
Fasteners lock geometry and transfer load firmly. Robotics set primary hardware, while technicians finalize torque and backup.
Localized cure tents create a stable microenvironment. Controlled ramp, hold, and cool cycles prevent thermal distortion. Ultrasonic and torque checks verify the joint's integrity. NDI must confirm no hidden anomalies before release.
At this stage, the aircraft is structurally complete, but still lifeless.
The engine must align perfectly with the airframe. Even minor angular errors affect thrust and vibration.
Mounts are torqued in sequence to distribute load evenly across the structure.
Hydraulics power flight controls and landing gear. Leaks or contamination are unacceptable.
Avionics modules form the aircraft's brain, BRU. Sensor fusion begins here. Bleed air supports environmental control and anti-icing done. Connections must withstand extreme temperature.
For the first time, the aircraft receives power. Before ignition, every line is pressure tested. Stability confirms integrity.
Programs are verified as maps. Predicted thickness guides every pass to avoid hot and cold spots.
Thickness is validated continuously prongtros. The map dictates the next pass, tooth by tooth. Sanding corrects waviness without breaching minimum coating thickness. Each pass is measured and reversible.
Coating, cure, and outgassing are tightly controlled by volatile compounds must stabilize to spec before any flight-critical tests.
Helmet and cockpit systems handshake, video overlay, latency, and alignment are validated.
Engine start follows a strict interlock sequence. Each step confirms readiness before ignition. Control laws and actuator responses are exercised through defined transients. Telemetry confirms nominal behavior.
Ground control loop active. Proceed low speed for control and brake checks.
Full power runs validate thrust, vibration, and thermal margins guide. Telemetry ensures structural and engine safety limits are respected.
Systems armed, HUD green, ready for departure.
Roger that. Cleared for takeoff.
Telemetry, sensor fusion, and pilot feedback close the loop. From idea to flight, the digital thread and craft converge.